Good day, everybody. Those of you that have enjoyed a number theory class would notice fairly quickly that this is related to a very well-known result. Let me just write it like this initially. And you see the pattern continues here. In other words, these are a bunch of factors that are just decremented by 1. Now, it turns out it's a little more useful to think of a prime number because that gives some structure. Okay, so you can replace this in with p minus 1. This would be p minus 2. This would be p minus 3. Now, notice that it doesn't end in 3, 2, 1, which makes it slightly more, a little bit more work because you can't use this result directly called Wilson's theorem. Now, I'll show you what I mean by that. There's a famous result, maybe the most, shall we call it the most important result in number theory, the necessary and sufficient conditions for a number to be prime. This works for all primes. You have to check it directly for 2. It's trivially true for 2, but this is true, mod p. And y'all, this is called Wilson's theorem, okay? So you see this result we have here is close to, or this thing we're looking for, is close to being in this form already. And we want to find out what this object remainder is when you divide it by 29. Okay, so let's move on down. Now, so again, this is the Wilson's theorem I just stated. See, we have this in the form p minus 1, p minus 2, p minus 3. And so this is in the form, okay? But this is the full Wilson's theorem, the full, here we ended in 4, here we ended in 3, 2. But from here, we can move on and state, since the 2 and the 3 are missing, we would say 6 times a, right? In other words, this object a times 6 is this object right here. So all I'm trying to say. So you see, if we can solve for a, we'll be done with the problem. And that's really fairly simple because of this notion of what we call arithmetic inverses. Notice that 6 times 5. Now, sometimes it's not this easy, okay, but 6 times 5 is congruent to 1 mod 29. That is, it leaves a remainder of 1 when you divide it by 29, okay? Okay, so that's very, very useful because 5 is what they call the multiplicative inverse of 6, okay? So again, if we multiply through by 5 right here, this just becomes 1a, and I'll write the 1 down. This 1 you see right here is the 1 that you see right here. We have 1a is congruent to negative 5. And of course, it's all modulo 29. But when we talk about remainder, we're not interested in a negative number, we're interested in a positive number. Well, the next one over that is 29 away that's positive, called the least residue, would be 24. Okay? And again, folks, this is mod 29. And that's our answer. Now, I'm not saying there's a unique answer to this. To me, that's the easiest one. But 24 would be the remainder. Okay, now what's the question? It says find such an x. Okay? Well, notice that that's fairly simple too, because 5, this part right here would have been 5x plus 8 would have to be 28. Okay, well, just right here, okay? So p 29, okay, just right here, let's just go 29 minus 1. I'll just write it down rather than talk. 29 minus 1 is equal to 5x plus 2. 5x plus 8, excuse me. Anticipating the answer. Okay, plus 8. Okay, and then if you do the remainder of this, you get x is equal to 2. That's very clear from inspection, right? Or is it, no, sorry. 4. Eraser. X would be equal to 4. And again, y'all, no claim that this is not the answer. It's leads to the answer. That's the remainder of 24, but this is our actual answer, 4. Okay, so that's what I got, ladies and gentlemen. X equals 4. difficult to check that by hand. You just have to trust Wilson's theorem. Okay. All right, folks, that is all. X equals, God, I'm going crazy. All right, let's see here. Eraser. X equals 4. Okay, such an X is X equals 4. Okay, again, I thought it was kind of nice. You got something that was algebraic looking. It didn't quite even look like Wilson's theorem then. Okay, but it really is. It's just the slight deception of leaving off the 3 and the 2. Then having to know something about multiplicative inverses is how I approached it. My approach may not be the best approach because there may be many times where it's difficult to find the multiplicative inverse for larger moduli. All right, that does it.